What's your deal?
All right, well, I'll get started. Hem. Hem. There, I think that's sufficiently many hems. Let me begin. So, Heavenly Father, we thank you for this time we have to meet together, study your creation. Just pray that you be glorified in what we do, and that we'd all understand a little bit more about determinants together, Lord. In your name I pray, Lord Jesus. Amen. So today we are doing determinants, and so hopefully today I will share with you the basic computational core of how we do that, as well as some of their properties, maybe prove a thing or two. So what is a determinant? So we have our so rather than giving you my definition, I'm going to first give you the formulas for the first few cases, all right? So determinant of a 1-by-1 matrix is just that. The determinant of a 2-by-2 matrix, A, B, C, D, is AD minus BC. We've seen that before, right? The determinant of a 3-by-3 matrix, let me use numbers this time, A11, A12, A13, A21, A22, A23, A31, A32, A33 is equal to A11, determinant of A22, A23, we're going to be here a minute, A32, A33, minus A12, determinant of A21, A23, A31, A33, plus A13, determinant of A21, A22, A22, A31, A32. Oi. 4-by-4. They don't pay me enough. Fine. 4-by-4. Determinant of A11, A12, A13, A14, A21, A22, A23, A24, A31, A32. Why am I writing this out? A33, A34. Why'd you guys do this to me? A41. I wasn't going to do this. A42. I'm going to regret this. A43, A44. Ay. Equal to, just kidding, sum I, J, K, L, epsilon I, J, K, L, A, 1I, A, 2J, A, 3K, A, 4L. I'm tired of writing those formulas. There's a simpler formula. Now, joking aside, the 4-by-4 expansion is on page 66. Right? So like on page 66 of my notes, if you look, I have an explicit formula for how the 4-by-4 determinant can be expressed as a alternating sum of 3-by-3 subdeterminants. All right. So, all right, fine. Let me. So this actually, fine. This is actually equal to A11. I'll at least start it, guys. A11 times the determinant of A22, A23, A24, A2, A32, A42, A33, A43, A34, A44. All right, then there's like minus A12 times the determinant of a 3-by-3 plus A 1, 3 times the determinant of a 3 by 3, and then minus A14 times the determinant of a particular 3 by 3. And let me just describe in words what's going there. Okay, so like I wrote the first one for you, right? So we've got A11, right, this guy. See that? And I'm multiplying it by the determinant of this 3 by 3. So that's what? That's the matrix with the first column and the first row deleted, right? So what do you think goes in the parentheses here? A with row 1 and column what? 2 deleted, right? And so forth. So like I can color code. What goes in here is this submatrix, okay? So, any questions so far? I'm just trying to share with you guys the base formulas for the determinant. What I'm doing right now, everything except for this right here is really my definition. All right, so let me give you the definition. The determinant of a square matrix is equal to the sum over I1, I2, all the way out to IN, from 1 to n, of epsilon, I1, I2, IN, of A1, let's see what I do. Yeah, A1, I1, A2, I2, A, N, IN. So what this is in words is the completely anti-symmetrized sum of the products of n entries from A. Now this funny looking epsilon symbol is the completely anti-symmetric symbol. So like epsilon 1, 2, 3, n is equal to 1. And anytime you switch a pair of indices there, it gets you a minus. So like, let me just show you how this works let me show you how it works in low dimensions so you can appreciate the formula. All right, so like the formula here, a little bit tricky. Actually, it's not. It's actually really not tricky. So in n equals 2, you have epsilon ij, right? And so you either got epsilon 1, 1, epsilon 1, 2, epsilon 2, 1, epsilon 2, 2. That's it. This by definition is 0. This by definition is 0. This by definition is 1. This by definition is minus epsilon 1, 2. But minus epsilon 1, 2 is minus 1. So that's it for the 2 by 2 anti-symmetric symbol. And if you look at how the determinant formula works for n equals to 2, you've got the sum over I and j from 1 to 2 of epsilon ij, a1i, a2j. How's that work out? Well, there's just two things. Epsilon 1, 2, a1, 1, a2, 2, plus epsilon 2, 1, a1, 2, a2, 1, which is a1, 1, a2, 2, minus a1, 2, a2, 1. That, my friends, is exactly the AD minus BC formula written with component notation, right? And if you do this for three things, then, well, there's a lot to list here, all right? So like, if you've got epsilon 1, 1 anything, if you've got epsilon 2, 2 anything, If you've got epsilon 3, 3, anything, these are all 0. Anytime you have a repeated index, see, because anytime you have a repeated index, it's equal to minus epsilon 1, 1i, minus epsilon 2, 2i, minus epsilon 3, 3i. So the thing is, by definition, if you switch any pair of index in the anti-symmetric symbol, by definition, it gives you a minus what you started with. That's how we define it. It suffices to define the value. If you define the value of the symbol for 1, 2, 3, dot, 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 n to be 1, that uniquely fixes the values for everything else if you agree that it's anti-symmetric in any pair of indices. All right? It's anti-symmetric in any pair of indices. So anytime I switch an index, I get a minus. So for example, 1, 1, I flip to 1, 1, I get a minus. If something's minus itself, it's 0, right? So this is 0. Anytime we have any repeated index in the epsilon symbol, it's 0. Yep.
Sorry, but epsilon, what exactly is it?
It's a combinatorial symbol defined by, it's 1 if epsilon 1 through n is 1. And then other than that, we define all of the values by antisymmetry of all the indices. So like I'm giving you the explicit definition for the n equals 2 case. There's only 4 things to consider. For 3, there's a lot more, because 3, how many values does 3 indices have? If they range over 3 things, 3 times 3 times 3, there's 27 things to consider here. So I'm not going to write them all out. I'm just trying to describe the only way we have 0 if any 2 of these are repeated. The only way you can have non-zero for 3 indices is for all 3 of the indices to be distinct. So you see, we have epsilon 1, 2, 3 is by definition 1. That's the definition. And then if I switch any pair of indices, right? So like if I do epsilon 2, 1, 3, that's a minus. And then if I switch the pair 1, 3, I get minus a minus, which gives me a plus. And then if I flip, let's say 2 and 3 here, I get that. Listen, I don't think of it this way. I'll just tell you what I think. So 1 is epsilon 1, 2, 3, which is equal to epsilon 2, 3, 1, which is equal to epsilon 3, 1, 2. These I call these are the cyclic permutations of 1, 2, 3. Basically, you're just taking the indices and pushing the last one back around to the front. See, I take the 3, I push it back around to the front. My bad. Wait a minute. The other way around. I push the 1 that way, back. Then I push the 2 back. Okay, so you can look at it either way. And then minus 1 is equal to epsilon 3, 2, 1, which is equal to epsilon 2, 1, 3, which is equal to epsilon 1, 3, 2. See, if you're counting down the indices and then looping back, then you get a minus 1. That's the pattern here, actually. So of the 27 possible potential values for the epsilon ijk, only these 6 are non-zero. But these 6 are things you've seen before, you see, because in Calc 3, you guys study A cross B, yeah? You study A cross B, the cross product of A and B. What's the formula for that? What it is the formula is A, let's see here, A2B3 minus A3B2, comma, A3B1 minus A1B3, comma, A1B2 minus A2B1. Or if you prefer, you could write this as, this is, I don't want to write it out again, but like the first one gets paired with E1, the second one gets paired with E2, the third one gets paired with E3, standard basis for us. So a formula for this is the sum over ijk from 1 to 3 of epsilon I, j, k, a sub I, b sub j, e sub k. That's a stone cold formula for the 3 by 3. I mean for the cross product. Yep, what I do?
Lower index is 3.
The what?
The lower index of the sum.
Oh yeah, that won't work. Thank you. I appreciate it. I'm setting 1 equal to 3 again, aren't I? At least you told me about it today. That's good. So look, so you can search check it out, right? If the k is 1, that's these terms, right? If k is 1, what's here? Everything except for 1, 2, and 3. How so? The anti-symmetrized such. See, 2 and 3, 2, 3, 1. Let's see if I did that right. Yeah, 2, 3, 1 is plus 1, right? But 3, 2, 1 is minus 1. These are exactly the plus minuses in the cross product formula. The difference between this and calculus 3 is the formula I just wrote on the board is completely legitimate. It's not this hybridized, like in Calc 3 we teach you to take the determinant of a 3 by 3 matrix where the top matrix is vectors and the lower 2 rows are numbers. That's technically speaking nonsense. From a perspective of naive determinant theory anyway. I mean, there's a way to make that formula rigorous, but who cares? But, well, this is it. I mean, to me, this is the way to make the formula correct. But so anyway, what I'm trying to say is the mathematics of the determinant is the mathematics of the cross product in some sense in 3 dimensions. They're both really given to you by the same combinatorial beast, namely the epsilon ijk symbol. There is another way to do this, which is to take the sum over all permutations. But do you guys know what a permutation is? No, so I won't do that. All right, so math majors learn something called a permutation. Mathematicians prefer to write the definition of the determinant as the sum over all permutations. So like there's another way. Okay, so listen, I know this is unfamiliar and weird and new, this formula. But this formula does give us a definition for the determinant, which works for arbitrary size. And it's actually pretty concrete, all right? Like, it's easy enough to prove things in this definition that would be really hard to prove in the other definition. For example, what would happen if you, like, instead of looking at the determinant of A, you look at like the determinant of A with like adding one column to another. You could look, trying to think how to say this easily. The quote-unquote multilinearity of the determinant is much easier to see in this formalism. So like the multilinearity of the determinant is the fact that if I was to say do a row addition, no, I really want to talk about column addition. I've been wondering when I would pay the price for not talking about column operations. I think it's now. Now is the time. Yep. All right. So some words here before I inadvertently erase things and forget to tell you things. So these things over here, these are called Laplace's expansion by minor. Laplace's expansion by minors. In fact, that's how Ley defines the determinant. All right. So the Laplace expansion by minors. Whereas the formula, our definition is, I don't really have a name for it. It's so, but I will call it our definition. Now, this is wonderful, but natural question you guys are going to ask is like, what is the determinant, right? So, easiest thing to think about, 2 dimensions. You got a square, right? I mean, square. Listen, you got a square. Here's its length. Here's its width, right? So if you look at the vectors, you got what? Like this guy and this guy. You could use these as sort of characteristic vectors, right? Like 0w and L0. What happens when you take the determinant of, L0 and 0w? What do you get? LW, right? So what is that? That's the area of this, right? It turns out this is still true. It's still true, like if you do it like this. If this is, like A1, A2, and this is B1, B2, and you take the determinant of, say, A1, A2, B1, B2, you get actually the area let me call this thing P. You get the area of P. That's not quite true. The reason it's not quite true is it actually gives you plus or minus the area. Where the plus or minus, how do you determine the plus or minus? Here's the deal. If A, by the right-hand rule, like if A sweeps to B in the counterclockwise sense, this is straight the area. However, if my picture is wrong, if the picture is actually like this, if the picture is like this, so actually A has to sweep counterclockwise into the other one, right? Then this formula actually will give you minus the area.
Sweep clockwise.
Yeah, clockwise. So the sign of the determinant, actually, if you put one vector first and the other vector second, the sign of the 2 by 2 determinant tells you whether or not the second vector is clockwise or counterclockwise swept from the first vector. That's what its meaning is. So positive for counterclockwise. And I guess we made clocks go the wrong way back in the day, right? Think about it. It's kind of like Benjamin Franklin and his stupid choice for charge. Idiot. So puts a minus. And for 3 by 3s, right? It's easy enough to see if it's a cube, right? Like if this is vector A and this is vector B and this is vector C, and they have length A, B, and C respective, right? If you take the determinant of just concatenate these dudes, well, it's just going to be ABC, right? That's the formula if they're actually perpendicular, which makes sense. It's the volume. More generally speaking, what this works out to, though, if they're not actually pairwise perpendicular, what you get, if you take the determinant of a 3 by 3 matrix with A, B, C, you get A dotted with B cross C. And that is actually equal to plus or minus the volume of the parallelepiped. With edge vectors A, B, C. And how do you just, when does it give you plus, when does it give you minus? Well, here's the deal. If A crossed into B points in the same direction as C, it actually gives you the volume. Because if C is in the, if you have like the situation like this, if this is A and this is B, A crossed into B, it's up, right? So as long as C is somewhere above this plane, you'll have A cross B dot C is positive. On the other hand, if the vector C is actually below the plane, then what happens is A cross B dot C is negative. So if A cross B is in the same direction as C in the, like, I guess to be technical, you could say the projection of the cross product the projection of the cross product of A and B in the C direction is parallel, not anti-parallel to C. If that would be a technical way of saying that. But if it's on the same size, then ABC is what I would call a right-handed triple. And in the sense that A cross B is in the same direction as C, generally. Now, to make it exactly the same direction, we would need that A and B are perpendicular, and we'd need that A cross B is actually parallel to C. Like that's, sometimes when people say right-handed triple, they're insisting that the vectors are pairwise perpendicular and that the third vector is the cross product of the first two. All right? So anyway. So determinant is area. Determinant is volume. The determinant of an n by n matrix is also the n volume. So the determinant gives us the general definition of what we mean by volume in n dimensions. Even in even the one-dimensional case, what's the determinant of a number? The one-by-one case, right? Its determinant of A is A. What is that?
The length.
It's the length of the number, right? But what? Plus or minus. So what's the sign of the determinant tell you there? It tells you whether you're to the right of 0 or to the left of 0. So the determinant's always a sign. Determinant is a signed volume, where the plus or minus speaks to the handedness of the vectors, which we're calculating the area for. But determinant, unlike the cross product, we can define for n vectors in n dimensions. Now, I do have some pictures in the notes which hopefully explain some of the things I was saying, more carefully. In terms of, I have a picture that actually breaks down the non-square case for this. Like you can make little triangles and shift things around and find a way to understand why this actually should be equal to a1b2 minus a2b1. There's a way of actually seeing it from shifting like little triangles around and such. It's an interesting thing to work through, but we have other things to do today. All right, so, and of course, if you remember Calc 3, what's the other place we saw determinants? Remember the Jacobian? That was the other place we saw determinants if you had Calc 3, is in the change of variables theorem, right? Because the change of variables theorem was actually about how we, basically how we change the differential. What is the differential, though? It's basically the measure of the area, or for a double integral, or the volume for a triple integral. So of course, when we change variables from one to another, the determinant's going to pop up because the determinant describes volume. Now, I wanted to do some numerical examples, but I need to tell you the properties of the determinants here. So let's write these down. This is proposition 3.31. Well, it's okay. So one of the things that makes determinants just so lovely is, we've been doing some kind of hands-off-ish stuff, like, I talked about span or linear independence. It's not a formula, it's a concept, right? So it's easy enough to get lost in that. But determinant, on the other hand, we're taking a matrix and we're finding a number which represents the signed volume of that matrix, right? That's it. It's a calculation. So that's usually a happier place for students. But there are a lot of moving pieces here, and this proposition, used wisely, will save you much pain, but ignore it at your peril. All right, like you gotta use these to make your life easier. So one of the things about determinant, and you can see this if you think about the 2x2 formula, especially. I have the. You can, if you look at the formula for the determinant of the 3x3 in the notes, you can also see this pretty well. I have a proof of this in the notes. Maybe at the end of class we'll look at the proof. So the determinant of the transpose is the determinant of the matrix. Here's another one. If there exists J such that row J of A is equal to 0, if there's even one zero row, guess what? This is wonderful. So watch out for this. If some sneaky professor puts a zero row in your matrix, and you're actually and it's a 4x4 matrix, and you're calculating out that monstrosity I just erased here, you're doing it wrong, right? Because if there's a zero row, the determinant is 0. In fact, let's think about this conceptually. If the determinant is calculating the n volume for n vectors, what's the n volume for n vectors if there's any linear dependence amongst the vectors? For example, 3 dimensions. You're taking the volume of the parallelepiped. What if those three vectors are coplanar? What's the volume of the parallel pipe bed?
0.
It's 0, right? So actually we can replace this. We can level it up with this. 3, if there exists a non-trivial linear dependence amongst the columns or rows of A, then determinant of A is equal to 0. Now that may not be my number 3 in the notes. Yeah, it's not. My number 3 in the notes is the much more boring, if there exists a 0 column, it's 0. Okay? So I'm going to put a 3 tilde. Right there. Feel better? The multilinearity I spoke of a second ago, I was trying to find a way to say in words what I'm about to write, and I guess I just couldn't. So here it goes. If you've got A1, A2, all the way down, and then we get to the kth one. In the kth spot, we've got A sub AAK plus BBK. So that's the kth column, and I've got constants A and B, and then that goes on to AN. Well, that's equal to little a times the determinant of A1, and then you've got AK, AN plus B times the determinant of A1, da-da-da, BK, AN. In other words, that we have linearity, you could say, column-wise linearity. So I can pull a number out of a linear combination here like that. And if I've got a sum of two vectors in one column, I can write it as the determinant of everything else being the same with the first vector, everything else being the same with the second vector. This is linearity of the determinant. Watch out. I don't think I've hit anybody yet this semester. It's good. Now this one will catch you off guard. Watch out for this one. What happens if we've got a scalar multiple times A? How's that work out? Think about it. That means that you're multiplying every column by K, right? So if you think about applying number 4 n times, what happens? Here, how about this? If I have the determinant of, like alpha A, alpha B, alpha C, alpha D, what happens? Alpha A, alpha D, minus alpha B, alpha C. We get alpha squared AD minus BC, which is alpha squared times the determinant of ABCD. So you see, if you pull a scalar out of a determinant, you don't pull it out once, you pull it out n-fold times. So that's how that goes. The antisymmetry of the determinant means that the determinant of B is equal to minus the determinant of A if we go from A goes to B by a row swap. If we row swap the matrix, it just changes the determinant by -1. All right. And 7, if you just do the kind of ones that we did for like the LU decomposition, we just get the determinants are equal. So this is just A goes to B by just a, how can I say this, row addition. And I don't just mean row addition, I mean like the ones with the scalar multiplication mixed in, right? Like row 1 minus 2 row 2 goes to row 2 kind of thing, all right? Row goes to row 1. So those are the properties of the determinant. Those are the, I would say, the elementary properties of the determinant. Let's see if time flies when you're having fun, Let's see here. So let's work out let's put these into practice. Let me show you some examples with numbers. Let's do something that's interesting, I guess. So let's see here. Example 1, I suppose. Let's calculate the determinant of 1, 2, 3, 4, I don't know, 8, 7, 10, 11, 7, 5, 7, 7, and 1, 0, 0, 1. So I'll tell you the wrong way to do it. Well, it depends on whether you see the pattern or not, right? So can you guys tell how I made this matrix? I'll tell you how I made it. The way I made this matrix was I wrote down the first 2 rows, and then I created the third from the first 2. So like, if this is A, then the determinant, let's see here, of how to say this. Oh, let's just do, see if I can, I'm trying to see if I can see it this way. So what if we do, I want to illustrate something. So 1, 2, 3, 4, if I subtract 8, I can do a row operation, okay? So minus 8 times row 2, we get what? 0, what we got? I'm doing row 1 minus 8 row 2. Rather row 2 minus 8 row 1. Sorry guys. So you guys help me out. What's row 2 minus 8 row 1 for that matrix? Oh, -1? Okay, yeah. And then -9, and then?
I meant for the second one, where it's -1 it was -9.
Oh, okay.
7 minus 8.
Cool. 10 minus 24, minus 14. 4 minus 88. Minus 84?
11. It's 11 minus.
Oh, I'm sorry. So what do I got? You guys help me out. What'd you got?
Minus 14 is good.
Yeah.
Minus 14 was good?
Yes.
Okay.
And minus,
So 11 minus 32, you guys said?
minus 21.
Minus 21. All right. And then we'll also do row 3 minus 7 row 1. See what that does for us. That gives us 0, -9. Oh, you're just saying that.
No,
You calculated, or you're just saying that?
it's working out that way.
And -21 on the last one.
Yeah, well,
Are you sure? Okay, well. Okay, so now why is this equal? I'm using property like 7. 7 says that a row addition doesn't change the determinant, all right? So at this point, we see that it's 0. See, because if any, so this is an example of a very non-trivial linear dependence, right? 2 rows matching gives you a linear dependence amongst these 2 rows. At the base of everything, the definition of the determinant is that it's anti-symmetric with any exchange of 2 rows or any exchange of 2 columns, actually. So if you have 2 rows are equal, when you exchange it, you get minus what you started with. But if you've got a number which is equal to minus what you started with, that has to be 0, since we're working over a field of characteristic 0. Well, we're not working over a field of characteristic 2 anyway. So that's 0. Now, that's kind of a nasty question in its original formulation, because if you didn't see this, you might be tempted to just calculate, right? But it seems like, it seems like just trying some easy row operations is maybe a good move for something like this, right? It doesn't cost you much to do like 2 or 3 row operations to see if it, uncovers some secret plot against you by the instructor, right? Yeah, okay. Example 2. what if we have the determinant of 1, 0, 0, 0, and then 0, 0, 1, 0, and then 1, 2, 3, 4, 5, 6, 7, 8. How would you go about calculating that determinant? So what I would do in this situation is, since I'm privy to the expansion, oh man, I erased it without labeling it. The formula I wrote, all of the formulas I wrote, the Laplace expansion by minors, those were all expansions across the top row. Those are expansions across the top row. So you can do a Laplace expansion by minors on any column or any row. I'll use my projector here and show you the formula for it in a minute, but I'm partial to expanding things across the top row. That's just like my default, you know? And so one thing I can do is just say, okay, well, I'm going to do a row swap. See, this is minus the determinant of 1, 0, 0, 0, 5, 6, 7, 8, 0, 0, 1, 0, and 1, 2, 3, 4 down here. So see, I just minus because I row swapped. You got that? All right, and then see how this goes? When you do Laplace's expansion by minors, only one subdeterminant can be non-trivial, you see, because I cross out that and that, but any of the other, well, not the subdeterminants, it's the coefficients on the top, right? So like A12, A13, A14 in the formula I wrote over there earlier, those are all 0. So in the expansion across the top row, only the first one survives. And so this is equal to minus the determinant of 6, 7, 8, 0, 1, 0, 2, 3, 4. Right? And then let me use the antisymmetry again. See, that's equal to minus a minus, which is plus the determinant of 0, 1, 0, 6, 7, 8, 2, 3, 4. So I'm going to keep using the expansion across the top row for the sake of this discussion. And so that is just minus 1 times the determinant of everything that's not in the first row and second column, which is 6, 8, 2, 4. So the answer is minus 24 minus 16, also known as minus 8. It would have been much more laborious to straight calculate from Laplace's expansion mindlessly across the original top row. Yeah.
What property changes the sign when you go from the 3 by 3 to the 2 by 2?
From here to here?
Yeah.
This is the formula I wrote out on the board over there, because we do like 0 times the determinant of 7, 8, 3, 4, minus 1 times the determinant. This is the minus you guys always forget with the cross product in Calc 3.
Oh, okay.
It's that same minus. It's taken many points from many of you. Don't let it take any more. 0, 6, 7, 2, 3. See, like I don't.
Oh, okay.
It's the minus and the plus. So let me project. There's something I need to show you guys. So, proving the equivalence of Laplace's expansion by minors and the epsilon formula, all right, or the sum over permutations formula. That is a very technical problem. There is a proof in my notes. You can read it if you want, but you're certainly not responsible for that proof. That is well beyond this course. So, we're in the position that we want to use properties of determinants, but we don't actually want to prove all of them, and that's okay. Oh man. So I guess I have to define something here. So like Cij, I believe, is -1 to the I plus j, and then we're looking at the determinant of A with row I and column j deleted. So Cij is, it's got this plus or minus factor, all right? And it's got the ith row and the jth column deleted. This is the so-called matrix of cofactors. And so this boxed formula right here says that you can write the determinant as a sum. You can use the cofactors, you can sum them across any column or any row, actually. So I think the one I have here, A1j, A2j, that's a sum across. What happens is you're going one, if your row index is going 1, 2, da 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 n, you're actually doing, that's down the what? That's down the jth column. So that's actually the expansion by minors along the jth column formula right there. But you could do it either along the jth column or the jth row. Again, the proof is somewhat technical. Here is another thing I wanted to show you because I don't want to write it out. To see that the determinant of A is equal to the determinant of A transpose, why do I have both places? So I have, these are all the terms, and if you just look at it, every place you've got 1, 3, you've got 3, 1, and like if you just sort things out, you can see that it's equal to the transpose just by explicit like looking at it, basically. Not a, there it is. All right, so let me get to the point here. So I have some simple examples in the notes just with numerics that, you'll need to do some of those. Here's another one where I have, so here, this is good. I've expanded down the fourth column. So the way this works, see the fourth column? I like the fourth column. Why? You do want to learn this expansion on a column or row idea because it simplifies calculation a lot. So like on the fourth column, I expand, which means that's what so if you look at that, 4 is in the 4, 4 spot, so I go -1 to the 4 plus 4. So that plus minus sign actually works out to a plus here. And then I do determinant of the submatrix form by crossing out the fourth row and the fourth column, which just leaves me with that. And then I expand across the second row of that one. So that is 2, 3. So I do -1 to the 2, 3, which gives me a minus. And there's a 5 here. And then M23 is my notation for the matrix with the second row and the third column deleted, which gives me that. And then, and then I use this, there's this trick, if you write out the thing again, you can do like, and then, but I don't have this trick. There's a trick. You guys know what I'm talking about? There's this trick for calculating 3 by 3 determinants by just writing the matrix out and then out again. And then if you just do diagonal slices, like, and you use pluses for those, and the other way, and put minuses for those, like a fruit math ninja, then you'll just have it. But I don't know. I don't have this formula memorized, and I don't know how to tech it. So here we are. Here's the properties of the determinants I was talking about. And the proofs are all in terms of this Levi-Civita symbol, the epsilon symbol. And they're just technical is all there is. I'll leave you with this. If we have a diagonal matrix, the determinant of a diagonal matrix is super nice because basically just applying the properties we just talked about, whichever one you like, you can either factor the d's out one at a time using the linearity of each column or whatever, but the long short of it is you get the determinant of the identity matrix. Something else I should tell you. What is the determinant of the identity matrix? It's just 1. That's right. So that will actually come from, if you look at my definition, the identity matrix has delta ij for the formula for each column. And so when you look at that formula, it just collapses down to epsilon 1, 2, 3, 4, da 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 n equals to 1. So to say that the epsilon 1, 2, 3 to n is 1 is actually just our way of saying the determinant of the identity matrix is 1. And that actually uniquely defines the determinant in n dimensions. The determinant is the unique alternating multilinear map which sends the identity to 1. So that's actually, mathematicians like that definition, but anyway, next time we will derive things like Cramer's rule and all kinds of other applications, believe it or not. So.